All right, so of course I started recording and I don't have my iPad connected, but we're looking at, this is the Unit 12 FRQ, and what is happening in this one is that it's kind of unexpected what they want you to do, because they're actually asking you to come up with the least squares regression line. Okay, I was just getting my iPad connected. So if you notice, it gives you a couple of tables. You can use your calculator to set up a couple of lists, create your scatter plot. I might just kind of talk about this one. So you would create, it already gives you this, but you would set up your scatter plot, and the question here is, does a linear model seem appropriate? So you would need to determine based on that, does it look like you have equal variance the entire way? Is it linear? And those are the main things you're looking for with the graph. Okay, so if you set that up, you would end up with some kind of a linear graph. You can use the data to construct a least squares regression line. Now, the calculator can do this for you. As far as showing your work on a question like this, what you would be doing is you would want to use some of these formulas from the very top part. And so you can actually show what your slope is, because you can take the first list. So for instance, if I come up here, I could plug this data in. I could plug this data in and I could get my mean for that, and I could get my standard deviation for that. Well, really, it's a sample standard deviation. And that's what I could use that, and this would be I'm predicting let me just double check. I'm predicting the output length from the dial setting. So this would be my X, and then this would be my Y. I could find right here. Now, the reason I'm showing you this, I'm not actually going to go through and do the math or do it on the calculator, but from here, if you're trying to show your work, how did I come up with the least squares regression line? Well, the slope of it is going to equal the correlation, which we could get from our least squares regression analysis, times S sub Y over S sub X. And if you already have that number here and here, you can actually plug that in. The correlation coefficient can come from your calculator as well. All right. So for the first part of it, it's kind of going back to just Unit 3 concepts. But then it gets to the bottom. Assume that all conditions for inference are met. Indicate the hypotheses appropriate to test whether there is a linear relationship between output length and dial setting. So they're just asking you to create your hypotheses. The null is that beta is equal to 0. And the alternative is that beta is not equal to 0. But you want to add context. What does beta mean in this? This is the slope. This is the change in output length for every change in dial setting. And then the last one right here, when it asks for if we have convincing statistical evidence that there's a linear relationship between these two variables, we're looking at the fact that there are, I'm going to go back up to the top for this. There are 8, right here you can see 8 trials. So we have N of 8, which means degrees of freedom for this will be N minus 2, which is 6. And what we want to do is we want to compare this 9.08018 to 6 degrees of freedom and an alpha level of 0.05. So I can just come over here to 6 degrees of freedom, find the 0.05 level, which is the tail probability up at the top. And you're going to see that that is a very significant number. In fact, it's the p-value here is less than 0.0005. So you can use that in your interpretation. That's about all I wanted to say to this, because I'm not saying it's simple, but there's some other ones we're going to have to spend some more time on. If you have questions on this, then maybe make note of it, and we can spend more time individually with this. Okay, let me close this one down, and let's look at unit 10 and 11. 10 is an interesting one that we'll come back to. 11 is actually very straightforward, and I might not even do this, but it gives a very straightforward table, and it wants us to basically run the inference test, a chi-square independence test. Or wait, this is a homogeneity test. Let me see. Yes, this is a homogeneity because look, we have two samples. We have a sample from the East Coast and a sample from the West. So this would be a test of homogeneity, but we run it the same way as a test for independence. And anyways, once we run that test on our calculator, you can draw your conclusions that are appropriate. I'm not going to say any more about this one. I'm trying to zoom out if I can. There we go. Number 10, this is one, both Unit 10 and Unit 9 FRQ that I assigned you guys. These are ones that are almost more like the investigative tasks, because they start off pretty straightforward, but the last parts of it get pretty out there. Okay, and it also introduces some new things. So if you looked at this, and hopefully some of you did, it starts off by categorizing bank customers, and then each category got its own sample size, sample mean, and sample standard deviation. And what is going to happen is that the bank manager is going to conduct multiple two-sample t-tests, each at a significance level of 0.05. So how many t-tests need to be run in order to compare all groups? And actually, I'll just ask that question to you guys. How many t-tests do we need to run if we have 3 groups? 3 of them. We're going to need to compare A and B, B and C, and A and C. So 3 t-tests, and I'll just answer this one quickly. So of course you would write out a sentence for that. And this is where it starts introducing some new not new concepts. Well, some of them are new. This is something we never ever talked about in class. But if you are running multiple tests, then you can get a type 1 error from any one of those tests where you incorrectly reject the null hypothesis. And the fact that this could happen on any one of these multiple tests means that we have what's called a family error rate for type 1 error. So if any one of these tests ends up with a type 1 error, then we have a type 1 error for our entire analysis. So a t-test, this just explains what a type 1 error is. Okay, so basically it says this: if the probability of S represents a statistically significant result, N represents a result that is not statistically significant, what's the value of P, the probability of N? And just to kind of go through this one quickly, if there's a probability of 0.05, which is our significance level, I will say this: suppose the null is true. If it's true, there's a 5% chance that we're going to incorrectly reject the null hypothesis. That is your significance level. We're saying this isn't likely to happen, but there is a 5% chance that it will. So what's the probability that we get that we do not get a statistically significant result? Well, it would just be the complement of a statistically significant result. So that means it's going to be essentially 0.95. Again, not super challenging yet, and maybe none of this is challenging. We'll see. But in the last question, it gets a little tricky. And you'll notice this was a Unit 10 FRQ, but honestly, this is dealing a lot more with probability. So, you know, If you have more questions on running a 2-sample t-test or z-test, then let me know. So this is not a specific table that we're going to use. This is just a hypothetical. Imagine that you're giving 2 t-tests. You could get a non-statistically significant result, and in the second one, it could be one or the other. Likewise, the first one could be statistically significant, and the first one could be yes or no, either way. So the family error rate is the probability of obtaining a statistically significant result for at least one of the t-tests. So we are going to figure out the family error rate for 2 t-tests, each conducted at a level of 0.05. All right. So here is just one approach that we can take to this. The family error rate, let me see if there's more we need to talk about. So it says use the tree diagram to determine the family error rate for 2 t-tests. Oh, for 2 t-tests, the family error rate is going to be if it's 0.95 that there's no statistically significant result and 0.05 that there is, and then that's true for all of these. Then here's what we do. We just multiply across and we can get all of our answers. So 0.95 squared is 0.9025. And we can see what's going on. I mean, I can multiply all this out, I guess I might as well. But, all right. All right. The only result that is good, assuming that the null hypothesis is correct, we don't want to reject it. This is the only outcome where we have never rejected the null hypothesis. It was not significant and it was not significant. So therefore we failed to reject the null, and that's exactly what we wanted to have happen. So these 3 represent any type 1 error that ever occurred in the process. So when we add that up, of course, we're going to get 0.970975. So it looks like our family error rate for 2 tests is 0.0975. All right. And you can pause, you can stop me if any of this isn't making sense. I know I'm kind of walking through some stuff pretty quickly. All right, so that was part C right here. Sorry, that was part part B2. Now we want to determine the family error rate for the number of tests identified in part A, each conducted at the 0.05. We don't necessarily need to draw a tree diagram because the only way that we're satisfied with this is if we don't get a statistically significant result, and we don't get a statistically significant result, and we don't get another significant result right there. I want to find that probability. So this is going to be 0.95 times 0.95 times 0.95. All right, I'm just doing that real quick on my calculator. And I get 0.8574. And if I get the complement of that, minus our answer, we get a 0.1426 significance level.
Is that way unknown?
So for this entire set of 3 significance tests, we basically have a 14.25% chance of incorrectly rejecting the null hypothesis. Again, I'll kind of stop there. Are there questions on this? Why I picked any particular number to use? Okay. So this is some level of challenging. And the last one is where it gets a little bit trickier still. Because now the question says, we don't like this 14.25% chance of getting a type 1 error. I don't think anyone would be happy with that. So we want to have a family error rate of 0.05. So we need to do some reverse engineering and figure out for any one test, what is the error rate going to have to be? Or sorry, what is the significance level going to have to be on any one test so that after we run 3 of them, we only have a 5% chance of a type 1 error? Well, this is where I want to show this again. We want to get 3 non-statistically significant results. And we want the complement of this to be, let me write this again. We want the complement of this to be 0.05. So again, we want to know the probability of not getting 3 straight statistically significant results to be 0.05. Again, are you with me on that? Right. So in this case, we want 1 minus the probability of 3 straight non-statistically significant results to be 0.05. And of course, now we can do our math and we can figure this out. And you might say, well, what math are we doing? We don't know the probabilities here. Well, I know that whatever the probability of n is, I'm going to do this 3 times. So I'm going to have the probability of n cubed. So if I subtract the probability, eventually when I do my math, probability of n cubed has to equal 0.95. So I'm just going to take the cube root of 0.95. All right. And when I do that, the probability for getting a non-statistically significant result has to be 0.983. Which means the probability of getting a statistically significant result has to be 0.017. And that's my significance level for any one test. All right. Feeling good? All right, I did get a question. How many questions are on the final? I can't recall right now. I will look that up before we're done, and I will let you know. I think it's somewhere around 25-ish, but I mean, I could be making that up right now. I'll give you the exact number in a minute. The last thing I wanted to look at was this fun problem right here, and this is one that is definitely like an investigative task. We need to set up and understand the context for this problem, but notice what's happening, that there's a fair die. It starts off straightforward enough, but there's a claim that says that if you bake a die for 200 degrees at 200 degrees Fahrenheit for 10 minutes, it ends up weighting the die, and you're going to have a certain side land up more often than the other. So they did that. They rolled it 200 times afterward, and here's what they came up with. Let me see, does it say? Okay, it landed 43 times on 6 after they did this process. Now that that's 21.5% of the time. They did their 95% confidence interval. So far, we don't even have to do any math. But does this interval provide convincing statistical evidence that the number 6 will land up more often on the baked die than on a fair die? So if I come up with what this confidence interval is, we start off not too bad. I want to figure out what the actual confidence interval is. So 0.215 minus 0.057 gives 0.158. If we add, of course, we're not as worried about this end of it. That's 0.272. So with this, we want to compare, in a fair die, we would expect 6 to be rolled 1/6 of the time. So 1/6 is 0.16 repeating. So maybe you guys can answer this. Does this confidence interval provide convincing statistical evidence that the number 6 will land face up more often on the baked die than on the fair die?
No,
No, it does not. And why not?
because 1/6 falls in the middle.
Perfect. That's exactly right. When we look at the interval, 0.16 is part of it, so it could land exactly as often as we'd expect. This could have just been a random fluke in how it was rolled. So,
And then, how many free response questions are on tomorrow?
no free response on tomorrow's test. I'm doing the free response right now just because that was part of our review. And of course, your test is on Tuesday, those of you doing the AP test. So I figure it's worth it kind of looking at some of these. If you are not doing this, this might be just, for fun, right? Because this is what you do for fun. Now, the next one says that a significance test was run, a hypothesis test, and there was a null hypothesis that the proportion of rolls was 1/6, which is no change. And the alternative is that they actually rolled more often. And they got a p-value of 0.033. Now this, I think we all know, because it's less than the significance level, we would reject the null hypothesis. We would say this is statistically significant. There is convincing evidence that the die rolls more often on a 6 than a fair die would. Okay, and that's where we run into a little bit of a dilemma. Like, why did we get a statistically significant result with the inference, with the hypothesis test, but not with the confidence interval? And we're going to investigate that a little bit. So I'm trying to figure out exactly how much details to go in on this, but I feel like it's good conceptually, so we might dig into this a little bit. Keep in mind that a 95%, any confidence level, let me say, is measuring from your point estimate in the middle outward. So you are getting the middle X% of data. So in a 95% confidence level, you have a middle 95% of data. But beyond that, you have 0.025 down here at the low end, and you have 0.025 up here at the high end. Okay, so that's your confidence interval. Now with the hypothesis test, we're saying that there's this 5% region up at the top that causes us to reject the null. But notice that this 0.025 and this one add up to 5%, but it's not 5% evenly distributed. Sorry, it is evenly distributed left and right. So that 5% is split between top and bottom, but in the significance test, all the 5% is up at the top, high end. So that's conceptually why we end up with one is a statistically significant result and one of them is not. It happens to fall in between this range between 0.025 and our p-value is right here, and then 0.05. And notice, of course, that's where it ended up. It says we got a 0.033. So it's significant in one end, or in one test, not significant in the other. So that's not exactly what the question is asking us. What they're saying is we want to find the critical values. And this is something we haven't talked about as much, so it's worth going into. The critical values aren't the Z, like the Z star, well, the critical value in this confidence level right here will be, of course, your these values right here is what they're referring to. What defines your interval? So that's going to be just the same numbers we came up with before, 0.272 and 0.158. Is that right? That sounds right. All right. So that with this particular one, and you end up with 0.215 in the middle. Sorry, I'm trying to remember all the numbers. Now, also you have your z-scores here of negative 1.96, 1.96, and then your 0 in the middle. Now right here, because we have a tail probability of 0.05 at the top, this is something that we haven't necessarily looked at on this table. At the bottom, you have your significant, your confidence level, but at the top, you have your tail probabilities. So what we want to do is we want to find a tail probability of 0.05, which is right here. And if I take this all the way down, my critical value down at the very bottom is 1.645. So the z-score oops, sorry. Let me erase that. The z-score that's associated with that is 1.645. And there you can see the difference. In the confidence interval, it was a 1.96 z-score. In the hypothesis test, it's a 1.645. Most of the time, this doesn't matter. This is kind of hidden in the background. But with this investigative task, they're actually bringing it out to the forefront. We're having to think about it more. Okay. Now, the actual value of x that represents that 1.645, this is where it gets a little bit fun. So let's remember that our population probability is 1/6, which I'm going to use just 0.16 repeating. All right, and then our sample size was 200 rolls, because I'm going to have to do some math here in order to figure this out. We need to remember that these are our numbers we're working with. And I believe that's it. So normally you have your test statistic equals p hat minus p divided by, and when you're doing a one sample proportion z-test, you end up with, you use the hypothesized proportion. So p times 1 minus p all over n. I'm sorry if I'm frying your brain, but trust me, I've fried my brain trying to think through this one already. So 1.645, now what we're doing is, rather than solving for the z-score, the test statistic, I'm saying here's the test statistic of interest. What p hat do I need to get in order to have a statistically significant result? So I don't know the p hat that I'm looking for, but I do know that 0.16 repeating, or maybe, well, I'll write it that way, is that is what the null hypothesis is. So now I'm going to have 0.16 substituted in here, 0.83 repeating, all over 200.
Wait, didn't they tell us what p hat was?
Well, we ended up with a p hat of 0.215, but this is something that's easy to forget, is that when you're doing the one sample z-test for population proportion, use the hypothesized proportion in the test. Don't use p hat.
Okay. Isn't it like 0.84?
Well, it will be 0.83 repeating. Yeah, so I mean, and it's going to be close enough with this. When you go through and do this math, I'm not going to make you guys plug this number in and do all the algebra, but you essentially get this p hat value right here is 0.210. So what that's saying is that if you get if you take a sample of 200 and you get a proportion, and you get a proportion of 21% or higher, then that is going to be considered statistically significant. So it's telling us, rather than saying, here's my result, let's run the numbers to see if it's statistically significant. It's saying, here's what is statistically significant. So do your trials, and then you can automatically know if it's statistically significant or not. It tells you what you're shooting for. All right. And again, that's not typically how we think of an inference test, but this is an investigative task, is making us think through things in a different way. Okay. I will also say this. With these investigative tasks, if you start being asked stuff and you get totally lost, give it your best shot. Don't take too long on it because you have 5 other FRQs besides this one to do. So just give it your best shot. And typically the first 2 parts of your parts A and B of the investigative task, you should be able to get some points from those. And so get your partial credit on the investigative task and do really well on the other ones.
And then real quick, the AP test.
Yeah.
So we're doing that here.
Here.
Like in the library, probably.
Yep.
And then if I need to like set that up.
It's like for your computer, your iPad.
Yeah, well,
You
I
won't-
set it up already.
You won't have to
But, oh,
because it's actually going to be pencil and paper test.
oh, well.
Yes. Yeah, it's one of the few. All right, so we came up with some things, and this is, part D right here. Joaquim, a third student, noticed that the confidence interval in part A gives plausible values of the parameter as an interval between 2 values. He suggested that they develop a one-sided confidence interval because they're only concerned with whether 6 was landing up more often than expected, not less. The one-sided interval will determine a value L such that all plausible values of P are greater than L. All right, the formula for L is given like so. And this is another thing. So they're throwing out a brand new statistic at us that we've never seen. And it's really kind of a one-off statistic that they're using here. So we need to determine the values of Z star needed to create the one-sided 95% confidence interval, then calculate the value of L. I will say this, I have not found the answer key to this problem. Normally these are all over the internet. And I was looking, I could not find the answer key. So everything that's happening so far is my best work to make sure I'm doing this right. So for this last one, it's still my best work to make sure we're doing this right. What values of Z star will give us the one-sided 95% confidence interval? And my understanding on this is that we want to have the confidence interval that says we can go from here to here, essentially. I'm not sure exactly where it would cut off, but we want 95% of our values to fall in there, in between those two, and 5% that we reject are going to be down here. And essentially we're saying on the low end, this can go to negative infinity and we don't care. Or more realistically in this scenario, I didn't mean to clear. More realistically in this scenario, because it's proportions, it can be a 0 proportion and we don't care. But we want to figure out what's the highest it can go to before we consider it statistically significant. And in my head, this doesn't seem too different from what we've already been answering. We want the same cutoff value to be true for the confidence interval and for the hypothesis test. So we should have a 0.210 up at the top as well. So if we go beyond 0.210 to the right, it should give us a, we should consider that to be a statistically significant result. It fell outside of our confidence interval, therefore it is no longer a plausible value. Okay. Again, this is like a pretty challenging one. You can see with the investigative tasks, it can get kind of challenging. If you like a puzzle, you'll enjoy this. But if you don't like a puzzle with a time limit, well then, yeah. So what value Z star is needed? Essentially, 1.645 is what we come up with. And that was one so that we end up with 5% of the area right here. Now let me just kind of wrap this up. And we can spend more time on this. We can try and work through it more if this is something you're like trying to wrap your head around and you get, anyways, if you're getting into this, we can kind of work on it more. But the very last question, it says, do these results of the one-sided confidence interval agree with the results of Aurelia's significant test in part B? So that was where they did the one sample z-test, and she got a statistically significant result. With this, we would get the same thing. We would say that the 0.215 is outside of our confidence interval. Therefore, it would be statistically significant in a sense, because it would not be within the 95% of values that we expected to find. It would fall in the 5% that we would not expect to find. Okay. And with that, I feel like I've lost track of what I'm even saying. Am I speaking English anymore?
Yes.
Okay. This is quite a challenging FRQ. Okay, I hope you guys looked at that ahead of time. I know not everyone did. So I just wanted to run through that. That's all we're doing today. I encourage you to do that practice test, do any and all of these practice FRQs. Get yourself ready. I will answer some of these questions about the final before we log off. I'm going to stop recording in just a minute. But the the multiple choice practice test, the answers are available online. So once you finish, you can feel free to check all your work on that. And that would be a good thing to do. And I keep saying, especially if you're doing the AP test. So with that, I'm going to stop recording, but then I will answer some questions about the final.